Hello everybody, good afternoon. Welcome to the REU NSF Research Experience for Undergraduates in Computer Vision poster session. We have these 11 very bright undergraduate students who have gone through this training for last 12 weeks. So today is the last day of their work here, and they are going to go through their spotlight presentation. After that, we will have the poster session. So I want to recognize two distinguished guests. One is Ross Henkel, who is the Dean of Graduate Studies here at UCF, and then Kim Schneider, who is the Director of the Undergraduate Research.
Hi, I'm Nicholas Baker from Johns Hopkins University, and I've been working with Nassim Soli this summer on temporal salience in videos. So just a quick introduction of what saliency is. It's essentially a predictor of human attention, particularly bottom-up before they have goals or tasks. What kind of draws the eye in a visual scene. So if you look at the two pictures there, the leaf is kind of what's drawing the eye in the visual scene. So in the saliency map, that's kind of what's picked out. So the goal of our research project was to apply this notion of spatial saliency and apply it to temporal saliency. And essentially what I mean by that is what frames in a video are salient, what frames are picked out as important. And those are probably the ones that are going to correspond to the beginnings of new events. So here are the results from the research experiment that we did this summer. As you can see, the red lines are kind of the ground truth of what we annotated as the beginning of an event. And you can see the model kind of picks out as salient the moment where those things begin. So if you take the derivative of any of these graphs, kind of the big part of local change is going to be the beginning of a new event. So we were happy with that, and that's what I've been doing this summer.
Hello, my name is Zachary Daniels. I'm a student at Lehigh University, and my mentor was Haroon Idris. My project focused on reconstructing cross-cut shredded documents. So you take a document and you cut it both vertically and horizontally into pieces of approximately equal size and shape, which we refer to as chads. And then all of these get put onto one image, and then we have to do some pre-processing to take those chads and try and find a framework to create the reconstructed document. So in order to do that, we first pre-process the chads, which involves segmentation, orientation correction, and we find various representations like the binary mass, derivatives, etc. And then we calculate a whole bunch of costs based on that pre-process step. And some of those include shape-based costs like edge correlation, gaps, overlaps. We also look at content-based costs like ruling line alignment and text line alignment, as well as some more semantic costs like bigrams and trigrams. In the end, we were able to reconstruct an 82-piece subsection of the document, and had we been given more time and faster computers, we probably would have been able to reconstruct the full document. And we've also been able to reconstruct a 25-piece subsection of the document in 235 guesses for a piece aligned with another piece. So thank you.
Hello, my name is Alla Petrakova. I am from UCF.
And I'm Steve Mussman. I'm from Purdue University.
We are working with Madi Kalia on understanding trajectory behavior, a motion pattern approach. Our algorithm addresses the problem of trajectory clustering. It is a well-established field of research in the field of data mining. Trajectory clustering seeks to understand the common behaviors from trajectory data, and by trajectories we mean an evolution in time of n-dimensional data. Some of the analytical purposes that this serves range from rule discovery to behavior classification and prediction, anomaly detection, and uncovering regions of interest. And some of the applications of this are traffic planning, urban development, tracking animal migration, and as you will see shortly, studying and analyzing Atlantic hurricane paths.
There are several different approaches to this trajectory clustering problem. One popular approach is to first define a similarity measure between the trajectories and then use a well-established clustering algorithm such as divisive, agglomerative, or spectral to cluster the trajectories. Another approach is to first break up the trajectories into segments and then cluster these segments. However, we take a new and different approach where we first convert the trajectories into something like optical flow and then use a variation of an algorithm, of a computer vision algorithm developed here at UCF to mine motion patterns. Here you can see our results on a hurricane data set where the hurricanes are from June over the last 150 years. The annotations provided by NOAA can be seen on the left as the white arrows. The results of our algorithm can be seen in the right two images, overlaid on the trajectories where the color corresponds to the direction, and the exact correspondence can be seen by the color wheel in the lower right corner. It can be seen that our algorithm recovers the annotations provided by NOAA. If you would like to see our results on other data sets and learn the details of our algorithm, you can come see our poster. Thank you.
Hello, my name is Kristina Peterson, and my mentor is Ray Ho. My topic is Exemplar SVM for Action Recognition. The Exemplar SVM looks at training an SVM classifier, a linear SVM classifier, based on one positive and many negative data samples. The motivation behind this is that you can reduce your labeled data set if you reduce your positive labeled samples. Negative samples are much easier to come by. You can use data mining to get them. So this is going to ultimately reduce that labor process. The approach is that we train the one positive sample versus the other action classes. And because the SVM output are not necessarily compatible, so we have to convert them to probabilities using Platt's method. So we have a sigmoid function and we are able to find those alpha and beta parameters and fit a sigmoid curve to it to get the probability function. And then we use our calibrated exemplar scores as mid-level features. The accuracies were able to approach the best reported results for this data set with the benefit of less required labeled data. Thank you.
Hello everyone, my name is Patrick Porson. My mentor is Haroon, and the title of my project is Deep Learning the Relationship Between Visual and Textual Data. And first I want to talk about the data set that we're using. We're using the MIR Flickr data set, which contains 1 million images and their tags. And 25,000 of these images have been annotated for 38 classes. Some example classes are bird, tree, and night. And a classic problem in computer vision is image classification. So given an image, we want to classify it into the 38 classes. And the problem that we explore is multimodal classification. So given an image and its tags, we want to learn a joint representation and then use this to classify the image along with its tags. And to accomplish this, we propose a multimodal stack denoising autoencoder. And in the top left, that's our model, and if you want to learn about how we train the model, come to my poster. And our results show that we do better than LDA and SVM, but not quite as well as multimodal DVM.
Hi, my name is Levi Smith. I'm here from the University of Central Florida, and my grad student mentor is Karam Sumro. Our topic is on improving concept detection by utilizing temporal relationships. So just a brief overview of our project is just that we aim to use the temporal relationships between concepts to improve concept detection over a temporal period. And we're going to do this by, rather than looking at a single concept in isolation, we want to take advantage of what we define as the causality between two concepts, which is simply how one concept can lead to or cause another concept. And we want to improve concept detection in general and have applied our methods to two data sets, the TrekVid and also a self-annotated soccer data set. Down here at the bottom, you can see how we define causality, which is similar to conditional probability, but with an added time constraint. So here on the right, you can see an example of that. You can see a corner that occurs, and then a brief period where no concept is occurring, and then a goal. All this occurs within a 12-second interval. So in this case, it would be said that corner has caused the goal to occur. You can see how this is stored in our causality matrix below, where you can also see, for example, that a goal has a high probability of leading to a celebration occurring, and also that a goal has a high probability of leading to another goal, which represents replay value, which is what the main diagonal along our causality matrix represents. So what we've done with this causality is use it to help correct for confusion in our classification probabilities and just to improve concept detection in general. Thank you.
Hi, my name is Shelby Thompson and I go to Marshall University, and my mentor was Enrique Ortiz, and my project was labeling faces within photo albums. So our problem was, given a Facebook photo album or any photo album really that you could find online, it's hard to tag or label individual people that are in that photo or in that album. So how do we identify and label multiple people in a photo album correctly? I used mainly HOG, K-nearest neighbor, SVM, and the PubFig 83 dataset. If you have any questions about my project, you can come to my poster. That's pretty much it.
Hello, my name is Alejandro. I'm from University of Central Florida, and my mentor is Amir Zamir. My project is GIS-assisted object detection. Pretty much, object detection is kind of plagued with a lot of false positives, and we aim to improve the results by using GIS data to assist. Usually what we get is on the left. We use DPM models to get our object detection. The results are kind of random in this case because we wanted high recall. We wanted to definitely get the true positives somewhere in the sea of false positives. And what we want, the traffic signs are the blue ones, and the traffic signals are the red ones. And what we want is on the right, and that shows one of our results. We implement a GIS fusion algorithm. We take the GIS data for various classes. We have classes for streetlights, traffic signals, traffic signs, trash cans, fire hydrants, and various other objects. And we project onto the image these GIS coordinates to get an estimate as to what the true arrangement would be according to the GIS data. You see lampposts, road signs, and traffic lights. And we use that data to sift through the false positives, and as well as kind of give a quantitative number to these combinations of bounding boxes, and we aim to find the minimum to find the best combination, and that shows our results for this one particular image. And that'll be all. Thank you.
Hello everyone, my name is Alvaro Velazquez. I'm a student here at UCF. My mentor is Nassim Soli, and my project is subspace clustering via graph regularized sparse coding. So what we were trying to do is use graph regularization to exploit the geometric interpretation of the data that is normally used in sparse coding. So here's the motivation. We applied this framework. This is a video without graph regularization. This is just sparse coding. You can see there's a lot of outliers and the patches diverge. But then when you apply graph regularization using the exact same algorithm, just with the graph regularization term, you get the much better results that are on your right side. So then we proceeded to attempt this framework on video segmentation. So what we did is we applied it to cuboids. So we attempted to segment videos using small cuboids, and you can see the results there in the algorithm. So essentially we just got all the geometric information of the data using a similarity matrix, degree matrix, and a Laplacian matrix, and this constitutes the graph regularization term that you would use. And that's it.
Hello, my name is Christian Wagon, and I'm from High Point University, and along with my grad student mentor, Karam Sumro, as well as another REU participant, Levi Smith, our project was improving concept detection by utilizing temporal relationships. And so the aim is to take advantage of these temporal relationships between concepts in order to improve overall detection. And we quantify these temporal relationships into something we call causality. And what that is basically how one concept causes or leads to another concept. We say that's true if they occur subsequently within a specific time span. So for instance, for the event of soccer, we would say that maybe a corner kick leads to a goal if it precedes the goal by, say, 12 seconds. We incorporated this notion of causality into 3 different methods. The first is an iterative approach, the second is a dynamic programming approach, and the third is our own Markov chain-inspired approach. And if you look at the bottom right of this slide, you'll see the graph architecture for our Markov chain-inspired approach. And what this is we can give this the SVM probabilities for concepts across different clips in a video. And along with these temporal relationships between the concepts, and it will generate updated probabilities for where the concepts occur inside of a video. And we find that this gives improvement across our different data sets. So, thank you.